Okay, welcome to the second session of the annual meeting of IFIP Working Group 1.6 on rewriting. And it is my pleasure to introduce our second invited speaker, Jörg Endrullis. So Jörg completed his PhD at VU Amsterdam in 2010 on termination and productivity. Later worked as a postdoc and now assistant professor at VU Amsterdam. He won several Best Paper Awards, in particular at RTA. And he has worked on a number of topics in rewriting, including termination, in particular matrix interpretations, one of the pioneers of the method, productivity, confluence, and today we will hear about Jörg's work on graph rewriting. Over to you.
Thanks a lot for the introduction and thanks for the invitation. So as you already mentioned, I'm going to talk about graph rewriting, and what I will talk about is joint work with Roy Overbeek and Alois Rosette, who are both PhD students at the VU Amsterdam. The basic idea of graph rewriting is, like in term rewriting, we want to replace some left-hand side by some right-hand side in a larger context. And in graph rewriting, of course, the left and the right-hand side are graphs. So here we have a host graph where we have an occurrence of the left-hand side as a subgraph. And there are some additional edges connected to this left-hand side. So the first question is the rule applicable in such a context? And the second question is, if it's applicable, how do we transform these incident edges? How do we reconnect them if we rip out the left-hand side and put the right-hand side in? Where should these edges be reconnected? And we will discuss that there are different frameworks in graph rewriting and different possible answers on this reconnection. And I will tell a bit about a framework that we have proposed ourselves recently. So there is various kinds of graphs that you would like to be able to rewrite. We have simple graphs, undirected, directed graphs, labeled graphs. They can be edge labeled, node labeled, or both. We have multi-graphs, hypergraphs, attributed graphs, Petri nets, interaction nets, and so on. So we do not want to make a separate graph rewrite framework for each of these. So we would like to define the graph rewriting framework on a more abstract level, uniformly for all of them, if possible. And therefore, it's a natural choice to go with category theory for graph rewriting. So to this end, I will have to tell a tiny bit about category theory. I assume that maybe not all of you know it, but I will keep it to the very basics. I will just talk about graphs and a bit about pushouts and pullbacks in the category of graphs. A category consists of objects, and we have morphisms, arrows between these objects. The category of graphs, the objects are labeled directed multigraphs. So this means that we can have parallel edges with the same label between two nodes. And the morphisms in the category, they always can be composed, and composition is associative. The morphisms in this category are graph homomorphisms. So we have structure preserving maps, and we also require that this graph homomorphisms preserve the label if the edges or the nodes are labeled. We will denote graph homomorphisms like this with numbers or names of the nodes, in this case numbers 1, 2, 3, 4 for tracing. So for instance, the nodes 1 and 2 are both mapped onto this node, which we denote as 1, 2. And the labels of the nodes or the edges will be denoted as superscripts. So you see here that 1 is mapped on a node that also has the label A. Likewise, 2 has the label A and is mapped on a node with label A. And this edge from 2 to 4, 2 is mapped here, 4 is mapped here, and this edge is mapped on this edge. So we have preserved the structure. We write this special arrow with an arrowhead also in the front to indicate that we have an injective graph homomorphism. So in category theory, that's called a monomorphism. The colors that we are using here, they are just a visual aid for the tracing, so that you know that the blue edge is mapped on this blue edge, the red edges are mapped on these red edges. So the colors don't really have meaning in the pictures. So what is a push out in the category of graphs? A push out, we start from such a span. So we have three graphs, G, H1, and H2, and we have morphisms from G to H1 and from G to H2. And now the push out is a cospan that makes this diagram commute. So this is a commuting square. What does this mean? It means that if we compose H1 followed by P1 and we compose H2 followed by P2, we get the same. So this composition is the same as the composition on the right. And we do not want just any cospan that makes this commuting, but we want a particular one. We want a universal object. So for any other candidate that makes this commute, we want that this candidate can be factored through P. So if we have another candidate Q, we want that there exists a unique graph homomorphism from P to Q that makes these two triangles commute. So the composition of P1 followed by U should be equal to Q1, and the composition of P2 followed by U should be Q2. If we have injective graph homomorphisms, then you can think of this push-out construction as a generalized union or a gluing construction. So the graph on the top is a sub-object of both these graphs. So this red part is here and it's here. And now the push-out will combine these two graphs, gluing them along this common sub-object. So in general, we will not have only injective graph homomorphisms. So in general, we have a situation like here where we have two nodes that are mapped on the same node here. Now, what is the push out if we compute the push out of this span? Let's have a look. So the push out combines this graph here with this graph here and glues these two graphs along the interface. So it glues these two graphs along the nodes 1, 2, and 4. And that's exactly what happens here. 1, 2, 4, that's the gluing points. This 3 with its two edges is just added in. This 5 and these two black edges are just added in. And since 1 and 2 are merged along this homomorphism, they also have to be merged in the result. So this, from here to here, we have to merge 1, 2, and this gives this loop on this node 1, 2. So you could also say that this push out is a kind of gluing where we merge without adding any junk. So we only add what is there in these two graphs, and we don't add any confusion. We do not merge more than necessary. The pullback is exactly the dual of a push out. So we start from a cospan, and now the pullback is a span that makes this square commute. So P1 followed by H1 is the same as P2 followed by H2. And again, this should be the universal object. So if we have another span that makes this commute, then it can be factored through P. So if we have another candidate, then there should exist a unique graph homomorphism U from Q to P that makes, again, these two triangles commute. Now, this is the same picture as on the last slide, and that's the case is here that we have a set-like category graph, and we have monomorphisms, so we have injective homomorphisms. Then in this case, basically the pullback is the inverse of the push out. So we can think of this pullback as basically computing the intersection, so the shared part in this image of these two graphs. In general, we will not have injective functions. So the general case is a bit more difficult. For instance, here we have two edges that are mapped on this blue edge. So here we have a cospan, and we want to compute the pullback. So the pullback you can think of in this general case basically as a fibered product, so a pointwise product. So the node 1 here has one pre-image here, one pre-image here. So we have 1 times the node 1 here. Likewise, node 2 has one pre-image here, one pre-image here. So we have it 1 times here, and node 4 the same. For the node 3, we have a pre-image here, but none here. So it will not be in the pullback. So the pullback can filter things out. Therefore, it's a bit like an intersection. Only if there's pre-images in both of these graphs, then we will have this also in the pullback. Now, the pullback can not only filter things, the pullback can also duplicate. So if we introduce here another node 2 with another blue arrow that is mapped on this blue arrow here. So both of these nodes 2 are mapped on this node 2 here. then the pullback will change. We will get a copy of 2, and we get a copy of these 2 blue arrows that are mapped on this blue arrow. So we have here 2 blue arrows, and for each of them, it's instantiated by these 2 blue arrows that we have here. So it's important to understand that pullback in general is not the inverse of a push out. So this is only in set-like categories if we have monomorphisms. So here we have 3 nodes. The graph homomorphism along this side merges the nodes 1 and 2, and the graph homomorphism along this side merges 1 and 3. So what's the push out? The push out glues things together that have to be glued together. 1 and 2 need to be glued together because of this. 1 and 3 need to be glued together because of this. So the push out will give us just a single node where everything is glued together. Now, if we compute the pullback of this cospan, now forget about the inner structure here. So we have 2 nodes mapped on a single node here. We have 2 nodes mapped on a single node here. So we have, like I said, it's like a fiber product, a pointwise product. So we have 2 pre-images here, 2 here. So we will get 4 pre-images in the pullback. Now I have to say where this 4 is mapped. 4 is mapped like this. So this is not the same that we started from, but due to properties of the pullback, we have a unique arrow from what we started from into this graph. That's the result of the pullback. So now that we have some basics of push outs and pullbacks, we can talk about the currently predominant approach in graph rewriting, which is the double push out approach. So this is a rule in the double push out approach. So we have a left-hand side L, we have a right-hand side R. And as I said before, we have to somehow define how to reconnect incident edges. And in the double push out approach, this is done by this interface in the middle. K is our interface, and we have a graph homomorphism into the left-hand side from K and into the right-hand side. So we can think of K as giving names to the nodes in the left. And then we also, due to K, we also know where these nodes end up in the right-hand side. So now if we say that the connections, the incident edges, the connections with the host graph can only be to these named nodes, then it's clear how we should reconnect them in the right. And that's exactly what the double push out does. So the double push out gives rise to a rewrite step from the graph GL to the graph GR if we have 2 such push out squares. So you can basically think of this middle graph here as the host graph without the pattern. And then if you do the push out here, you glue in the pattern L into the host graph. And if you put a push out here, then you glue in the right-hand side into the host graph. Let's have a look at an example. So this is our host graph without the pattern. And now if we compute this push out, then we will glue this left-hand side into this host graph along, so we glue at X and Y. So this gives this result. Now, if we do the same and we glue in the right-hand side, so we compute this push out, then because the nodes X, Y are merged to the same node here, this edge C will turn into a loop on this merged node. So this is currently the predominant approach in graph rewriting, but it has several limitations. So maybe before saying something about limitations, let's say something about what we can do. We can remove nodes. So here the node Z is removed. We can add nodes and edges, and we can merge nodes. What are the limitations? One limitation is that we cannot duplicate things. So you may wonder, what if we allow this morphism from K to L, if we don't require this to be injective? So let's say that we merge nodes along this homomorphism. So what happens then? Here we have some host graph where we have a single node that appears in the host graph. So now what should this graph GK be that gives rise to this push out? So we have to find the graph GK that gives rise to the push out GL. So finding GK is also called finding a push out complement. And the problem here is that this answer is not unique in this case if this is not an injective function. The problem is that we can have this graph GK, which gives rise to this pushout, or we can also point this edge from Z to Y. We can likewise point to X, and it will give rise to the same pushout. So if this graph homomorphism is not injective, then rewriting this pushout complement is not uniquely defined, and rewriting becomes non-deterministic. And what you also see here is that what we've done here is not a duplication, but it's a non-deterministic distribution of the edges that we had before. So what we would like is, we would like to have a duplication that really duplicates a node, including all the incident edges. Another drawback of the double pushout approach is that you have hardly control over the embedding of the left-hand side in the host graph. So what do I mean by this? The only control you have is what you put in the interface. And nodes that are in the interface, they can have arbitrary connections with the host graph, with the context. And nodes that are not in the interface cannot have any connections with the context. But since we don't have control over what connections X and Z have with the context, so it can be arbitrary, so we can also have cycles here. In particular, we can have directly an edge from Z to X. So this rewrite rule actually simulates a string rewrite system. AB rewrites to BA. So as a string rewrite system, this is terminating. But in DPO, this is no longer terminating because we can apply this rule on a cycle. And DPO does not have any means to prevent such an application. So DPO cannot control the embedding of the rule in the host graph, or has a very weak control over the embedding in host graph. So I've mentioned before that this computing GK, computing the pushout complement, is a problem. So indeed, it is a problem not only if you allow this to be non-injective. So in general, we have given a rule and we have some match in the host graph. And then we want to know what is the rewrite step generated by this match. So we want to find GK, and this is called the pushout complement. But in many categories, this pushout complement is actually not uniquely defined. And this problem of having a unique pushout complement introduces heavy restrictions on the usability of DPO. So if you look in the literature, then actually many applications of DPO require adapting DPO itself. So these applications of DPO for a certain category then choose a very particular pushout complement. So while DPO looks like a uniform framework, actually, if you look closely, then this is a bit cheating because these pushout complements are often picked in a particular strategy. So examples of this are, if you, for instance, use the category of simple graphs. So now we don't have duplicate edges with the same label between two nodes. Then already, if this is our left-hand side, just a node with a loop, this is our host graph, node with a loop, this is our interface, just a node, then this pushout complement is not uniquely defined. We can have a node without a loop, will give rise to this pushout, or we have a node with a loop, gives rise to the same pushout, because if you have two loops here, in simple graphs, these edges will simply be merged because we cannot have multiple edges between the same node. Another example where things are complicated with DPO is if you want to have wildcards, if you want to allow relabeling. So if you want to have a wildcard label that matches any label. There actually have been papers in the 80s which were later found to have mistakes in the characterization of the pushout complement. And a paper that has done this correctly is a paper by Habel and Plump in 2002. So their method works with DPO, but they have to introduce very heavy technical restrictions to make it work. They have to choose a particular pushout complement, and also they have heavy restrictions on the shape of the rules. For instance, if you then use a wildcard in the left-hand side, you also have to use a wildcard in the right-hand side. So the question is, can we do better? So can we make graph rewriting work without these complications that come with the pushout complement. There are several other approaches. So there is a single pushout approach. So I'm not going into details of the single pushout approach, but basically it allows the left-hand side to be replaced in any context. So in DPO, you're not allowed to have incident edges connected to nodes that are not in the interface. In SPO, you can have this. And it will simply drop all the edges that would be left dangling by the replacement. The hash-queue pushout introduces some duplication, and the framework agree introduces duplication with a filtering mechanism that you can also, that you don't have to duplicate everything, but you can pick what you want to duplicate. But all these approaches have one drawback. It's very few control or no control over the embedding in the context. So all of these that are listed here, they allow the rule to be applied in any context. So as soon as you see the left-hand side pattern occur, no matter how the context surrounding the rule looks, the rule can be applied. And these approaches are destructive, so dangling edges will be erased simply. So we were wondering whether we can do better in the sense that we can make a graph rewriting framework with a very fine-grained control over the embedding in context and over the transformation of this embedding. So this is what we started from. We wanted to replace a left-hand side with some incident edges by a right-hand side. And the question was, how do we reconnect? And we have seen that the frameworks DPO and SPO answer this on a framework level. So DPO says that all of the incident edges must be connected to nodes in the interface, and all of these edges will be preserved. SPO will simply delete all the dangling edges. So in 2020, we have introduced the patch graph rewriting framework, and this gives much more fine-grained control over the application. So when is a rule applicable in a certain context, and how is this context transformed? So here we have a rule enriched with these dotted edges, and these dotted edges have names. The idea of these dotted edges is they stand for a set of edges in our host graph. So for instance, X here captures a set of edges with an arbitrary label from this node on the top to this node here. So it captures C and B here. This Y captures an arbitrary set of edges from the context to this node on the top. So it captures this edge D here. Z captures an arbitrary set of edges from this node into the context. So it captures this E here. And then by simply reusing these variable names, we can very precisely specify how these edges should be reconnected in the right-hand side. And we can also duplicate. We can say that this set of edges X should be put from this node to this. So they are in this direction, and this set of edges X should also be put from this node to this node. And we can say that this set of edges Y here, D, should be connected to this node on top, but also copied and connected to this node on the bottom. So you see here, D is connected to this node and D is connected to this. And this set of edges X, this CB, is from this node to this and from this node to this, copied twice. So we can drop things. Z is dropped, this E is dropped. We can duplicate, and we can fine-grained decide where we want to reconnect things. So on the category of graphs, this is much more flexible and much more general than DPO and SPO. However, it has also a drawback. We did formulate this using a set theoretic approach, so it does not easily generalize. So we were looking for a more elegant algebraic characterization of such a system that gives this fine-grained control. And we have presented such a framework this year at ICGT. It's called PBPO plus, so pullback pushout plus. Pullback pushout, the plus stands for strong matching. So as the name already suggests, we base ourselves on an existing approach, PBPO, by Corradini and colleagues. And I will explain what it means that we extend this with this strong matching. So a rule in PBPO plus looks now like this. So on the top, we have something that looks similar to a DPO rule with an interface, which is mapped in the left and an interface mapped in the right. But now we have also graphs L prime and K prime that belong to the rule. And we have here a square of graph homomorphisms that need to form a pullback. Now, in the examples, we will often also write the graph R prime in this corner here, which is simply the push out of this span. The reason for indicating this R prime in examples, it's formally not part of the rule. It's also not needed in the rewrite step, but R prime gives an indication what happens if we apply this rewrite rule to L prime. So it gives an indication of what the rewrite rule does with the pattern and the context. Now, how does a general rewrite step work? The idea is that our host graph is now sandwiched in, so our host graph GL is sandwiched in between L and L prime. So L is the pattern that has to appear as a subgraph of our host graph GL. And L prime is a type graph that restricts the shape of the context surrounding the pattern. So the L prime tells us how the host graph can look around the pattern. Now we have here a co-span now, and we can simply form a pullback for constructing a graph GK. So what does this pullback allow us to do? We have already seen a pullback can filter things out, so we can remove parts of the host graph, and we can duplicate things from the host graph. So we can duplicate and remove. So this is a kind of extraction step. Now, having done this extraction step, we get a span here from K into GK and from K to R. Now, from this span, we can compute a push out. Now, this push out allows us to extend the graph, add new things, and to merge things. So this is an extension and merging step. So in this together, this pullback for extraction and duplication and this push out for merging and extension gives an extremely powerful formalism. So this is our rewrite step that we obtain. We have now a rewrite step from GL to GR. And we have extended this with a strong matching condition. So this L is embedded, the left-hand side pattern is embedded in the host graph, but it's also embedded in this type graph L prime. So we have an embedding of L into L prime. Now, if we compute the pullback of this span, we require that this gives this identity along this line. I'm not going to go into details. I will just show an example what this strong matching does for us. So here we have a PBPO plus rewrite rule that removes an arrow from an isolated node. So we see here we have a node in the pattern with an edge, with a loop. And in L prime, we define that, okay, this is the pattern, and we can have some context. So this node Y will capture the entire context. So anything else we can map on Y, as long as the context is not connected to this pattern node X. So if we would have edges here, then it would not be of the shape required by L prime, because we don't have edges between X and Y here. If we would want to allow X to be connected to context, we would need to add additional edges here in L prime. Okay. So L prime enforces that this is really an isolated node and all the context is mapped on here. So I'm saying that all the context is mapped on here, but how do we know this? This we know by this strong matching condition. So the strong matching condition forbids mapping of context elements onto the pattern in L prime. Now, if we compute the pullback here, then what we see is the context is just preserved. This Y is the same as here with the loop. But the X, we filter out this loop. So indeed, we remove the loop from the single node. So this rule indeed does what we intended it to do, removing a loop from an isolated node. If we look at PBPO without the strong match condition, then we can map the entire context on this node X in L prime. And what happens now if we compute the pullback, it will filter out all the edges mapped on this edge here, and that's all the edges of the graph. So then this rule drops all the edges of the entire host graph. And you can actually prove that PBPO without the strong match condition is not able to formulate this simple rewrite step. So PBPO without strong match condition is not able to remove a cycle from a single node. You can always map the entire rest of the context onto this single node in the pattern and then drop all the nodes in the graph. all the edges in the graph. So what we see here is also that we have here some node y in L prime that kind of captures the entire context. And this is very handy to have. And we would like to have such a node y that can capture entire context, also in the case of labeled graphs. But in labeled graphs, this is difficult because then the edges here could have different labels. So we would need to enumerate all possible labels, so an edge basically on y for every label that we can have. So is there a better way to do this? Yes, there is a better way. We will slightly adopt the category of graphs. So what we would want is we would like to have in our type graph L prime, we would like to have some wildcards that can capture elements with arbitrary labels. If we work in graph, we cannot do this. We have to enumerate all possible labels. So what we are going to do is we are going to change the category. The objects stay the same, but we change the morphisms. So we will relax the notion of graph homomorphism. So instead of requiring that the identity of the labels is preserved, we simply say that every element should be mapped on another element that whose label is at least as big as the original label. So that's why smaller equal for the labels now. So the label of the source should be smaller equal than the label of the target element. So let's have a look here. So we have some partial order on our labels. So let's say that A, B, C were our original labels. And we now include a partial order. So the easiest way to do this is we introduce a bottom and a top element, and this gives us a complete lattice. So the bottom element now, it's smaller equal than all the elements in our lattice. This can be the source. So this can be mapped onto any element with an arbitrary label. So we can map bottom on B, we can map bottom on C, whatever we want. And the top element can serve as the target of any mapping. So we can map B onto bottom and C onto bottom. So the onto top. So the bottom can serve as a wildcard in our pattern L, and the top can serve as a wildcard in our type graph L prime. Now we don't need to use only this flat lattice. We can use an arbitrary complete lattice. So we can, for instance, have a lattice that has natural numbers and it has Booleans. So we say that all the natural numbers are smaller or equal than n. And then if we in our type graph L prime specify that we have here n, then we can only map natural numbers or n onto this edge. So we could not match Boolean true or false onto this edge. So why do we want this to be a complete lattice? The reason is that if we have a complete lattice, then the pushouts and pullbacks all still exist. So if we have a complete lattice, then the pushouts and pullbacks, structurally, they work just like in graph. But with the labels, they do something different. So in a pushout, if two elements are mapped on the same element, then it computes the join, the supremum on the labels. And if we do a pullback, then we compute the meet, the infimum of the labels that are mapped on the same element. So let's have a look at some examples. But before looking at it, mention that this category of graph less equal does not work with the standard approach DPO, with the standard graph rewriting approach, because the category graph less equal is not adhesive. And we've already talked about the problem. The push-out complements are not unique. So if we have this push-out square, I can put here a top, the push-out, so the supremum of top and top is top, but I can also put here a bottom, and the supremum of top and bottom is top. So the push-out complement is not unique. Using this category with DPO would give to non-deterministic rewrite steps, so the labels of the result would not be uniquely defined. But luckily, we don't need push-out complements in PBPO+. So in PBPO+, it works very smoothly. Let's have a look at some examples. This is a simple example of relabeling a node that has an arbitrary label. We overwrite this label with C. So we use this, what we call flat lattice. We have A, B, C, and so on. And we have a top element and a bottom element. So here we have in the pattern a node X with the bottom as label. So this can be mapped onto a node with an arbitrary label. So for instance, on a node with label A. And in the type graph that describes the shape of the host graph, we have the node with a label top. So again, a node with an arbitrary label could be mapped on this one, this node. So indeed, this X can be in the host graph a node with an arbitrary label. This node Z here in this L prime captures the context, and the context can be of an arbitrary shape. So all of the other nodes we map onto Z. This is fine because we have this edge here, so they can have arbitrary connections between themselves. We can also have arbitrary connections between this node X and Z because we have edges forth and back from X to Z. And we could also have arbitrary edges on X itself. So this rule is really applicable to any node in our graph. Now, if we compute the pullback here, so this graph K prime is almost the same as L prime. The only difference is that we have here a bottom, whereas here's a top. So the pullback computes the infimum on the labels. So the infimum of A and bottom will give us bottom. So the label is erased. And the infimum of B and top gives us B. So the label is preserved. So we can use bottom in K prime to erase labels, and we can use top in K prime to preserve labels. Now, if we compute this push out, then we get the supremum of the labels. So this C here is, so this node is mapped on this node with C here, and it's mapped on this node with bottom here. The supremum of bottom and C will give us C. And this part here is just glued in by the push out. So we have replaced the node with an arbitrary label by a node with label C. This is a more complicated example that shows several features of PBPO+. So here we have a pattern, a node labeled with A that has an edge to a node with an arbitrary label. And indeed, this can be arbitrary. Here we have a bottom, and here in the type graph we have a top. So any label could be mapped in between here. So in this example, it's a label B. Now this type graph here specifies how our context can look like. So we can basically map the entire context on this node 3 here. The connections of the pattern with the context are not arbitrary. So we can have arbitrary additional edges from 2 to 1. So you can think of the nodes and the edges that are in L prime but not present in L as placeholders for an arbitrary set of nodes or an arbitrary set of edges. So this blue node is, this blue edge is a placeholder for an arbitrary set of edges from 2 to 1. So we have here 2 edges mapped on this one. And this red edge in principle is also a placeholder for an arbitrary set of edges. So we could have arbitrary edges from 2 to the context. But we cannot have edges from the context to 2, and also not edges between 1 and the context. Also not edges on 1 itself, on 2 itself. So this type graph gives a very specific shape how the context surrounding the rule can look like. Now let's have a look at this cospan, what happens here. We see that the node 1, so the node 1 has pre-image 1 here and has pre-image 1 here, so we get 1 instance of 1. What happens to the label? The label is the infimum of A and bottom. The infimum of A and bottom is bottom, so we erase the label. The node 2 has 1 pre-image here, has 2 pre-images here, so the node 2 is duplicated. What happens to the labels? Here we have label B, here we have label bottom, so this label is erased. Here we have label B, here we have label top, so the other copy, the label is preserved. And the context is just copied because this 3 with this loop is the same as here, so the context is just copied. This 2 blue edges mapped onto this blue edge. In the pullback, we have here 2 blue edges, so we instantiate them because here we have 2 blue edges. This in the pullback is instantiated by 2 edges here from 2 to 1, and also from this copy, we have this blue edge from 2 to 1. If we would have wanted to drop, so make a copy of 2 without having these blue edges, then we can simply have dropped this blue edge here, and these 2 blue edges would be gone from GK. So now if we look at this span, we can compute a push out. So what happens here, we merge the nodes 1 and 2, and we have here label D, and we have a fresh additional node 4 with label E. So if we compute this push out, then indeed we have to merge 1 and 2. So this blue edges here turn into loops on this node. The push out computes the supremum on the label. So we have bottom, bottom, D. The supremum will give D. This is just glued in with label E. This part 2 here, we get the supremum of B and bottom, which will give B. And the context is just glued in from GK into the result. So we can remove things, we can filter, we can duplicate things, and we can also merge things. So this is a quite powerful mechanism. And you can use this to simulate string and term rewriting in a termination preserving way. So here we have, for instance, one way to simulate a string rewriting system, BA rewrites to AB. So our pattern are 2 nodes labeled with BA and an edge between, and our type graph L prime defines how the context around this can look like. So the context left of our string AB is mapped onto X here. The context right of it is mapped onto Y. Now, if we compute this pullback, so this graph K prime is almost the same, but we have the labels AB are overwritten by bottom, and this edge in the middle is removed. So if you do the pullback, then the labels AB are removed because the infimum of A and B with bottom is bottom, and this edge is filtered out due to properties of the pullback. And the rest is preserved because this context is just the same here, and this context is just the same here. Now in the push out, along this morphism, we reintroduce the labels AB and we glue in again an edge. So we get the supremum of bottom and A, which gives us A, and the supremum of bottom and B, which gives us B, and we have the edge again. So we indeed have a rewrite step from this graph to this graph. So we can think of this as rewriting ABB AB to ABA BB. And the crucial point is that this is really a termination preserving simulation of the string write rule, because this L prime enforces that these 2 context parts that we have, the left and the right context, they are not connected with each other except through the pattern. So the pattern cannot lay on a circle. So we can, in PBPO plus, we can very nicely specify that a rule is not applicable on a cycle. And we have very fine-grained control. We could, for instance, say that we would want to allow edges from the left context to the right context, and we just add in an edge here, and this would be allowed. If we want to allow cycles, we can add an edge from Y to X, and we could allow cycles in this way. But if we specify the rule like this, then this rule can be applied in arbitrary graphs. So the graphs can contain cycles inside then the context X or the context Y, but the pattern itself does not lay on a cycle. And we have shown that this encoding indeed preserves termination. And more generally, this encoding can also be done for term rewriting, where we then have nodes that capture the context above a term, and we have nodes that capture the substitutions, and we can then simulate arbitrary left linear term rewriting steps. So we can simulate arbitrary left linear term rewriting steps. Still, we have proven that this preserves termination only for left and right linear systems, so linear term rewriting systems. The problem with duplication is, so in principle, we can do duplication, but the problem with duplication is ill-formed graphs. So you can have disconnected components, and these disconnected components could then duplicate each other. So we think that there is hope that one could change the encoding a bit to maybe circumvent this problem. But for the moment, we've just shown that this simple, straightforward encoding indeed preserves termination. So what is our goal with this? Our goal is not to translate term rewriting systems to graph rewriting and then develop a stronger termination tool. But what this shows is that PBPO plus can be considered as a strict generalization of at least linear term rewriting systems. And that's already quite big class. And we can in PBPO plus not only have this kind of well-founded structures, but we can very fine-grained say that we want, for instance, to allow edges from the substitution X into the substitution Y. So we could say edges from here to here are allowed, or we allow edges from Y to the context above, but not from X to the context above. So we hope that this formalism, it allows to very precisely specify where are cyclic structures allowed and where are well-founded structures. So this is a nice generalization of both DPO as well as term rewriting. So this gives rise to challenging termination problems. So we have, of course, we have a large body of research and termination on well-founded structures, on terms. We have also a bit of research on termination on cyclic structures. So I think of cycle rewriting or DPO rewriting, and names that come to mind are Santema, Brüching, König, Waldmann, Dershowitz, and Joanneau. But at the moment, these are kind of separate things. At the moment, we have research on well-founded or research on purely cyclic structures, but there's hardly any research on rewrite systems that combine well-founded and cyclic. So maybe the only research that comes to mind is research done by Joanneau and Dershowitz. They have worked on graph path orders for their track systems. So this is another graph rewriting formalism. And in this graph path orders, they decompose the graphs into strongly connected components with well-founded structure in between. But then if they analyze this graph path orders on the rules, whether this is indeed decreasing, they have to consider all possible ways of cycles between what they have sprouts and they have roots. And in principle, you can have arbitrary connections between all of this. So they don't have fine-grained control what kind of connections are allowed. So they could, for instance, not say that we are allowing connections from Y to the context, but not from X to the context. So PBPO Plus has more control, and we are currently working on termination methods. One of our future works that we have in mind is also investigating whether these graph path orders can be extended to PBPO Plus, then making use of the knowledge where cycles are allowed and where not. So we hope that this can yield a strong method on this kind of general graph rewrite systems. And in general, I think that this is a nice field of research also for term rewriters, because this is an extension of term rewriting. So the question is, what methods of termination from term rewriting can be extended to allow for certain cycles? So maybe some of the termination methods for term rewriting can be extended to this formalism as well. So to summarize, we think that PBPO is a very nice framework for graph rewriting. We think it's much simpler than the predominant approach DPO, because the double push-out needs this push-out complements, which are really troublesome objects and introduce heavy restrictions. We only have pure pullbacks and push-outs along monomorphisms, so we have very simple ingredients of this method. Also, this method PBPO Plus, at least that's what we strongly believe, generalizes, so it subsumes, strictly subsumes all the existing categorical frameworks that are there. So it subsumes SPO, DPO, SESQ pushout agree, and it also subsumes PBPO Plus. This might be a bit surprising because it subsumes PBPO. This might be a bit surprising because we extend PBPO with an additional criterion, with an additional restriction. But this restriction is needed to enhance the control over how the pattern is embedded in the graph. So it prevents that we map context elements onto the pattern. And this additional control gives more power in rewriting. So we are quite sure that this indeed holds in the category of graph, that this is a strict subsumption. And we think it also holds in topoi. But formulating this on the most general level possible is difficult because all these frameworks have different assumptions about the categories that they work in. So for instance, the category graph less equal that we've seen is not a topoi. So we still are looking for a nice general formulation where this subsumption holds. But we think that it holds in almost all categories. PBPO Plus allows for very powerful relabeling, so we can have very powerful wildcards in our rules. it works absolutely complication-free with graphless equal, whereas DPO has troubles to do relabeling and it does not work with graphless equal. We think that PBPO is nice because it is a strict generalization of linear terminal writing, including preservation of termination, which does not hold for the frameworks that were there before. So these frameworks were not strong enough to exclude applications on cycles, and therefore going from terminal writing or from string writing to graph rewriting usually lost termination. Yeah. Further than this, we are interested in future work in studying also confluence for this. We are interested in meta theory. So for instance, concurrency theorems, if you have two sequential rule applications, can you make a single rule combining them both? And yeah, so there's a lot of research to be done. Thanks for your attention.
Thank you very much, Jörg, for a very nice talk on your ongoing project on graph rewriting. So we have a few minutes for questions. So if there are questions from the audience, raise your hand, or given this a small group size, just open your microphone and speak.
Yes, I wonder how you can you automatically prove termination of small examples in your new framework?
And not yet, we are working on it. So
we are working on that.
Yeah, we are working on that, and we hope to have in a few months, we hope to have some first version of some small termination tool that then will.
And what are the typical ingredients? You are looking for a kind of path order?
Yeah, so path orders is something that we have in the future. We are at the moment, we were looking at pattern counting. So, so just that you have patterns, assign a weight, and then you want to show that the counting of these patterns, that this weight of the entire graph, that this is decreasing. This already, it sounds easy, but it already turns out to be quite tricky to do. Yeah, so maybe it's we could at some point talk offline about this.
And in many versions of rewriting, you have a kind of monotone algebra characterization. So in term rewriting, you have a term rewriting system is terminating if and only if there exists a compatible monotone algebra. Do you also think that something will be the case for this new format? And what would be the notion of monotone algebra?
Yeah, so that's really unclear. So it would be marvelous if you would have some if and only if theorem for termination of graph rewriting. But at the moment, I think this is still yeah, far in the future. I'm not sure. So I don't have ideas how this should work. It's I think at the moment, so for the completeness, I don't have hope at the moment. I hope that we can define certain examples. So we have some examples that you have also worked on, interpretations of graphs with cyclic structure, and Dershowitz and Joanneau have worked on these graph path orders, which decompose a graph into cyclic parts and well-founded parts. So our hope is a bit to combine this, to use these interpretations that you have for the cyclic structures that you have also worked on, and these graph path orders to get the combination of these termination methods. But I don't have hope that this will be a complete method.
No, but if you can deal with many examples, it's already valuable. Okay, thank you.
Thank you. More questions? I see Vincent's hand, so please go ahead.
Jörg, I only saw the last half hour of the talk, but I hope you didn't answer this, but given Hans's question, no. So in term rewriting, we have, well, it generalizes a bit his question. In term rewriting, we have the foundation formed by Birkhoff theorem. So, and then the determination, well, the completeness of the monotone algebra is just a special case of that. So what about models in general? Do you have notions of model which you use, or do you have this correspondence between conversion and some kind of logic to prove things the same?
I think there must be work on this. I'm not entirely sure in how far this is developed. I think that models of graphs is already difficult exactly because you don't have this algebra, because you need a well-formed structure.
Yeah.
There are ways of there is graph notations where graphs are denoted as some kind of word, and then I think they have models for these kind of things, but I'm not sure whether this works for. Yeah, so I've seen some work in this direction, but I'm not sure in how far this answers your question. Yeah, I would have to look to search.
And maybe, combining Hans and my question a bit. So when you do examples by hand, do you have some kind of intuitive notion of counter model or something which you work with? Or is it really always at the syntactic level that you're working at this moment?
At the moment, it's on the syntactic level that we're working with. I think that the work of Santema, they use weighted type graphs to give an interpretation to graphs. Mm-hmm. I wonder whether this could probably be used as a counter model. If you have an interpretation that keeps that you show stays constant while rewriting, I think this should work. So I think that this method of Santema, Brugger, and Koenig on this using weighted type graphs for giving semantics to graphs, this should be applicable. But I don't think you will get the Birkhoff-like completeness theorem.
Okay, no, but well, anything at the moment is already a good. Okay, thanks.
Thanks. More questions? I would have a question. Oh, Vincent, please go ahead.
No, I was just waiting for others to have questions. So if you have a question, please go first.
Okay. So my question would be, you mentioned that linear term rewriting is subsumed. You also mentioned your framework has the ability to at least duplicate nodes. So is there a chance you could have duplicating rules?
Yeah, so duplicating rules are in principle no problem. So you could just make a copy of this in this K prime, and it would duplicate the entire substitution, this entire subgraph. So the problem with termination preservation is really that if you want preservation of termination globally on all graphs, then it breaks down, because if you have two disconnected components in the graph, then you can map, so then they can basically duplicate each other. Because you can map a disconnected component into this Y prime. If you would duplicate this, then the entire disconnected component would be duplicated. So, so in principle, duplication is no problem. And if you apply this to graphs which correspond to terms, then you have also the preservation of termination. But if you want termination on all graphs, including disconnected and ill-formed, then it gets troublesome.
Okay, so the non-standard interpretations in that sense would cause trouble.
Yeah, so the ill-formed graph, so to say, yes.
Yeah.
So it depends really. For termination of terminal writing, we have hardly methods that are applicable to local termination on a certain set of starting terms. But maybe for termination of graphs, this will be different. The type graphs already can be used to restrict shape of graphs. So maybe this could be that there will be local termination methods for graphs. So then it's also interesting to not only look at preservation of global termination, but then it would be enough to have preservation of termination on certain shaped of well-formed shapes of graphs.
Yeah, local termination, I think, is an underexplored topic in general in rewriting. So that sounds like interesting future work. Then, okay, we have time for another question. Vincent?
No one else? Yeah. So my own interest in graph rewriting mainly comes from functional languages, interpretations, their lambda calculus, this body. Do you aim for that at the moment? There's this whole transformational approach to transforming, functional programs via term into graph, whatever, rewriting. Do you want to cover that chain of transformations, or do you, for the moment, focus on term rewriting
No, we are definitely interested in looking also what other formulations you can simulate in PBPO class. So also lambda calculus or higher order rewriting or functional programs would be very interesting to look at. Yeah.
Yeah. So, and then the first thing that comes to mind is, of course, the pointer representation of lambda terms. Do you foresee any problems there, or?
We have not looked into this yet, so
Okay.
I don't know. So yeah, beyond the duplication, I'm not sure whether there's more problems to. Yeah, I cannot say yet.
Okay, thanks.
Okay. Thank you very much again, Jörg, for your nice talk.